Hey AP Chemsters, this is Mrs. Vanderwall with the next edition of the Blank Wall series. So we are done with section 17.2 and we are on to section 17.3, cell potential, electrical work, and free energy. Now if you remember back at the beginning, what did we define that E as? It was the potential difference. We also called it the electromotive force. And if you remember anything about force and work are related if you remember your physics. And the idea of this EMF is being a volt. Remember what we defined a volt as. So a volt was equal to joules over coulombs. Okay, so we defined that earlier, and we see we're going to use that definition again. So there is a relationship between joules and volts. And joules goes back to the idea of enthalpy, and we had joules being as part of Gibbs free energy unit as well. So they're all related. So we talk about work leaving the system has a negative charge. So like our battery, what kind of battery we're going to have? We're going to have a negative charge. So what's happening here? We define that little squiggly E is the same thing as a capital E, is negative work over coulombs. Rearranging the equation, negative work equals coulombs times the cell potential. And that coulombs is equal to N times F. N is your number of moles of electrons you get from your half reactions. And F is a constant. It's called a Faraday. And it's defined as 96,485 coulombs per mole of electrons. So you see we're going to be using those numbers. So you don't have to memorize them, but it's kind of handy if you do. So if we were to actually use this cell potential, the EMF, not all of it's going to be converted to work. Some of it's going to be lost due to heat, maybe friction. But the maximum amount of work is very useful for calculating efficiency of conversion. And so we can talk about the maximum work is negative Q times the maximum potential. So how is this related to free energy? Back in chapter 16, if you remember, we talked about Gibbs free energy. And wait for it, you know it's coming. Hang on. Here he is. This is Josiah Willard Gibbs. He didn't go by his first name. He was just known as Willard Gibbs. He was the one that we talked about for the Gibbs free energy, how much actual work is able to be done, and how much useful work is what we define it as. And he is actually one of the few Americans in this whole series of scientists. He was born and raised in New Haven, Connecticut. He spent his whole life pretty much at Yale after he got his doctorate there. He got the first doctorate in engineering, believe it or not. So anyway, he's the one that made all these relationships. So let's kind of go back to our problem now. Hang on. So you can kind of see where I'm going with this. If the W max is delta G, we can substitute what was our definition of work max is negative Q times the cell potential max. And then we substitute what Q is equal to is negative FE. So to put it all together, this is the equation that you really need to know and that we're going to use a lot. So Gibbs free energy is equal to negative number of moles times Faraday, which is the constant, times your E potential. So notice, remember what we said in the summary of section 17.2? We said that E, in order for it to be spontaneous, has to be has to be positive. And we learned in the last chapter that if the delta G were negative, the reaction would also be spontaneous. So here is that relationship between the spontaneous Gibbs free energy and the spontaneity of the cell potential. And that is why there's that negative number in front of the F, so that the signs are going to work out. So let's go ahead and do problem number 9. Problem number 9 is calculate the delta G naught at standard conditions for this following reaction. Is this reaction spontaneous? So what do we have to do here? I don't have all that information about delta G. I don't know if I can actually calculate the products minus the reactants. Excuse me, I don't have all that. What I do have, however, is the cell potentials on the a couple pages prior to this one. So let's go ahead and look at the cell potential, come up with the half reactions, and let's calculate E naught. Once I do that, I can plug it into the equation and calculate G. So why don't you at least pause this for a second, look up your E potentials for your copper +2 and your iron +2, and let's put that to work. Ah, get it? Put it to work. Ha, ha, ha. Go ahead and do that. Okay, let's see how you did. Well, as written, here is my reduction, I'm sorry, here's my oxidation, my mistake here. And let's kind of start this again. Let's do my reduction. That was right, that is my reduction. Sorry, I had a senior moment there. And this is my reduction. And so we looked up the C for the, or the E for the cathode. And when I looked it up, I got 0.34. We have used that already. And next we had iron. We haven't done a lot with iron though, have we? And it ends up being oxidized. So my C at my anode, sorry, my E at my anode, second time done that, is equal to negative 0.44, but that was also a negative number. And so when I put this together, notice I don't have to do anything funky with my electrons. They are the same numbers, so they do cancel out. Notice my equation is also balanced with number of atoms, and the charges all work out. And so my E of my cell is equal to positive 0.78 volts. Okay, so I at least calculate that, and notice what the sign of my cell is. My sign is a positive 0.7. So because it's a positive number, I'm kind of thinking it's spontaneous, but let's calculate G anyway. They told us to do that. So delta G naught, the formula is negative N F times E. Well, the question is, what's N? How many electrons were transferred? That's why you have to do this half reaction to do that. That's this number. That's this number. What is your total number of electrons being transferred? And that's 2. So it's negative 2 moles of electrons. And remember what a Faraday was? That was 96,485. And a Faraday is defined as coulombs over moles of electrons. Notice that the moles of electrons are going to cancel out. And now we're going to plug in the E value, which was the number that we just got right here. So times 0.78. Now, do you remember what a volt is? A volt is a joule over a coulomb. So I'm actually going to put that here. And notice what happens. In my equation, moles of electrons cancel out. Coulombs cancels out. And what's the only unit remaining is joules. Does that make sense? And the answer is, well, it should make sense because that's what Gibbs free energy is going to be calculated in. So if you actually get out your calculators and do the math, you'll get negative 1.5 times 10 to the 5th joules. Now, normally we think of Gibbs free energy in kilojoules, but in this case, that doesn't make any difference. The reason being, all they're asking is it's spontaneous. So notice that delta G naught is a negative number. Therefore, it must be spontaneous. And there you go. Let's try the next problem. Predict whether or not 1 molar of nitric acid will dissolve in gold metal to form a 1 molar 3+ solution. So notice, let me write this down. It's gold metal. So we want gold to become gold ion. That's the question. Will it dissolve it? What are they really asking you? Is it spontaneous or not? All right, so I need to go and actually look up something here. So let's go back to our chart and try to find nitric acid. Well, if you look on this chart, I don't see nitric acid anywhere. So what am I supposed to do? Well, perhaps this will help you. Isn't nitric acid where you take HNO3 and it 100% dissociates into H plus NO3 minus? Does that maybe help you a little bit? Let's kind of look here. And, oh, I think I found it. That's what we find. Here is your nitrate ion, and here's your H pluses. They dissociated. All right, so here this is at plus 0.96. And then what? We got to find gold in all this. Where's my gold? Let's see here. I think it is, oh, I found it. Here's gold at plus 1.50. So having this, let's go back to the problem now. All right, so let's do this. We have, let's copy down that equation we had. And so that's my reduction because that's what they want us to do. So if they want gold to dissolve, that's going to be oxidized. They want gold to become gold 3 plus 3 electrons. And so my E of my anode is equal to, I have to reverse the sign. Remember, if it's an anode, reverse the sign, negative 1.50 volts. Now, if you were actually doing this problem, you really ought to, go ahead and let's balance this out. But is that really going to answer my question? No. My question over here is, what is my E naught for my cell? That's going to tell me my answer. And when I do that, I get negative 0.54 volts. So if E cell is negative, what does that tell me about delta G? Delta G is positive. Is it spontaneous? Not. Okay, so that answers that question. No. So if I put gold in nitric acid, nothing's going to happen. It will just sit there. It is not spontaneous. All right, finally, for problem number 11, and that's the last one of the section. This takes actually a little bit of doing. So hopefully remember something about your delta G values, and hopefully remember something about making up your half reactions. So we need all that in order to answer what is the E naught for this reaction. Well, the first thing is go ahead and solve for delta G. Remember that it was your sum of your products minus your sum of reactants. Go ahead and do that now. You don't need me to help you. All right, hopefully you got this when you just did your products minus your reactants. Putting in the numbers that it gave us, I found the delta G of formation is negative 702 kilojoules. Now, if you remember our equation, though, what's the equation that relates Gibbs free energy and cell potential? Delta G is equal to negative NFE. I have the delta G. I have the F. It's a constant. Whoops, I didn't mean to do that. Wonder why I did that. Negative N, holy cow, NFE. I have the delta G, I have the F. I'm solving for the E. What don't I have? I don't have the N. I need to know how many electrons are being transferred. So I need to go and write out the oxidation numbers here to know which one is oxidation, which is reduction. Write my half reactions to know my N value. So let's go ahead and do this. If you remember your rules of your oxidation numbers, oxygen here is going to be negative 2. Oxygen here is 0 because it's in standard state. Oxygen here is negative 2, and oxygen here is negative 2. So actually, oxygen is going to be reduced. It goes from 0 to negative 2. That's going to be 1. So what's being oxidized? Is it my H or is it my C? Well, if you go back, H here is, I'll use red for H, plus 1 and plus 1, which leads us to our carbon. If the carbon dioxide, I'm over here, if carbon dioxide has 2 oxygen at negative 2, carbon is plus 4. Over here, if oxygen is negative 2, and I have 4 plus 1s, then what must carbon be here? Carbon must be negative 2. Go ahead and do that math again. If you add up the oxidation numbers here, negative 2 in the red, plus 4, because I have 4 hydrogens, minus 2, that's your oxygen. So your carbon is what is being oxidized. So let's go ahead and do that. Let me write it out and then go for it. Okay, I'm running out of time, so I'm going to talk fast. Notice my electrons are 6. That's your N. Let me go ahead and finish solving for delta E. All right, here it is. Solve for delta E, plugged it in. I got 1.21 joules over Coulomb.